tonight we're going to talk a little bit about rectifier circuits. We're going to start with a quick review of diodes. We're going to talk about what they are, a little bit about bias. We already talked about the curve a little bit, and we'll talk a little bit about the homework. Then we'll go into our lecture for rectifiers and power supplies, talk about what they are, why they're important. We'll do a quick review of what their goal is, and we'll do a block diagram of every the basic layout of every power supply. We're going to be talking about rectifiers tonight and power supplies next time. So this will be an introduction so you guys see where we're going. And we'll start talking about the rectifier portion. We'll talk about 3 different types of rectifiers tonight. And then next time we'll see how those rectifiers can be used in real split mode power supplies where you get both positive and negative power out of one supply. Okay? And then there's a little bit of homework. You need to do the diode crossword. You can take a look on the Canvas page and see the homework listed there as well. Okay? So we're going to move kind of quickly through the lecture tonight. Tiffany's presentation was great, but it took a little bit of time, so we need to move a little bit quickly. So I'm going to try and go kind of fast, but please stop me anytime if something is not clear, okay? So let's do a brief review of diodes. So anybody remember what a diode is? What's the basic function of a diode?
One-way
electrical valve.
Yeah, a one-way valve for electricity. Yeah, it allows the electricity to flow through in one direction and it blocks it in the other. So if you have a voltage like this, where it's positive on the anode and negative on the cathode, is that forward biased or reverse biased?
Forward.
Forward. Perfect. And does the electricity flow or not?
Yes.
Yes, it flows. So how much voltage do we have across the diode approximately?
0.7 volts.
0.7 volts. Exactly. Excellent. So that means that this diode is reverse biased. No electricity flows. And the voltage across it is whatever voltage you apply. Okay? So that's the basic review of diodes. That's what they are. That's a little bit about how they work. So we had some homework problems on diodes. I know I said I would do a couple of homework problems, but the presentation ran a little bit longer than I expected. So I think we'll put off the homework until next time. It's not due. You guys are welcome to work on it, but you don't need to turn it in at any time in particular. So I'm going to hold off, and at the beginning of next lecture, I'll do some of those problems for you guys, and we can review them. Okay? So questions about diodes before we move on? Yeah?
When you said the voltage on the reversal?
It's whatever you apply. So
it's a voltage drop, right? We're measuring across the diode?
Right. The voltage is always measured between 2 points, so the voltage across the diode is whatever voltage you apply. So if you have a 10 volt supply, you can have 10 volts across there. Yeah.
My question is, there's some diagrams like power supply, resistor, reverse bias, diode, and goes to the ground.
Mm-hmm.
The circuit, if reverse bias is not passing electricity, the circuit is not passing electricity. The circuit is not closed, right? How can you say he's not passing electricity?
Okay, so that is a good question. So let's take a second and we can look at that. So I know that's a little bit confusing. So I think you're talking about a circuit like this where you've got a power supply that's, say, 8 volts. You've got a resistor up here that's like 1 kilo ohm. And then, a diode like this that is reverse biased, and then that's connected over there. So this is positive voltage there and a negative voltage there. So this diode is reverse biased, and then we're asking what is the voltage at that point between those 2 points, right? So basically what's happening is that this diode is reverse biased. And like you mentioned, no electricity is flowing through. So it's essentially acting like it's not there at all, right? No electricity is flowing through it. It's acting like an open circuit there. That's pretty much how it's behaving. And so you're left with a situation like this. So there's no path for electricity to flow from one side of the power supply to the other, right?
Right.
So another way of saying that is that there is no current flowing through the diode there, or I'm sorry, through the resistor there, right? So if there's no current flowing through the resistor, we can use Ohm's law to figure out the voltage across the resistor, right? We say V equals I times R. So this is 0 times 1,000 ohms. So how much? 0 volts, right? So there is 0 volts across that resistor. Okay? So in other words, the voltage on one side is the same as the voltage on the other side. So if we have 8 volts there, how much voltage do we have over there?
8 volts.
8 volts. Yeah. So we've got 0 volts there, so that means 0 volts over there. So the voltage difference between the top and the bottom is 8 minus 0, or just 8 volts. Okay? Does that make sense?
Tricky question.
Yeah, it is. It's a little bit tricky. You have to kind of wrap your mind around it. Yeah.
Repeat that very last edge. What is that? How do you get the 8 volts?
Okay.
Oh, just across?
Yeah, the difference between one side and the other. Voltage is always a difference between 2 points, remember. So you look at how much voltage is on one side and how much is on the other, and then you take the difference, and that's the voltage between those 2 points. Yeah. Other questions? Okay, cool. So that was a brief foray into the homework. We'll do a few more examples next time if you guys have more questions. Okay, so then let's go on and talk a little bit about power supplies, rectifiers and power supplies. We'll talk about power supplies first because rectifiers are a part of a power supply. So we'll talk about what a power supply does, and hopefully that'll help us to understand why rectifiers are important. So the general block diagram, well, the general goal of any power supply, a DC power supply, is to take a high voltage AC signal that might look something like this, and convert that into a lower voltage DC signal. So that might look something like that. Well, it would be lower voltage, so something like that. Okay. So that is what they do. The reason that we do this is because power in the wall is transmitted as high voltage AC. So when we get the power, we get it as high voltage AC. But electronics typically require low voltage DC, like 5 volts or 3.3 volts or something like that. If you're using a USB charger, that's 5 volts. A lot of electronics, microcontrollers and things use 3.3 volts now. So we need to take the high voltage AC that comes out of the wall and turn it into the low voltage DC so we can use it to power our electronics. So that's what power supplies do. That's the goal of a power supply. We care because they're everywhere. Basically, anytime you have an electronic device, it needs a power supply to go from the AC to DC. So computers have them inside. Like we said, phone chargers have them, battery chargers, pretty much anything that is an electronic device and is plugged into a wall has some kind of power supply. So they're everywhere, so that's why they're so important. So let's talk about how they actually do this conversion from high voltage AC to low voltage DC. Basically, they do it in a couple of steps. They sneak up on it. So what they do is they take the high voltage AC and they convert it into a lower voltage AC. And they use a particular type of device to do that. The symbol for this device looks like this. Anybody remember what this kind of device is?
Transformer.
Transformer, exactly. So a transformer is a device that takes an AC signal and either increases or decreases the voltage. In this case, it's used to decrease the voltage. So after the transformer, the signal looks something like this. It's the same frequency, but lower amplitude. Okay, so the transformer decreases the amplitude.
Still AC.
It's still AC, exactly. So after the transformer, we need to get a little bit closer to the DC that we want. So we have this other device called a rectifier. So the rectifier takes the AC signal and it takes it gives you a signal that's only positive. So we'll see that different rectifiers give us signals that look a little bit different, but in general, all rectifiers give you a signal that's only positive coming out. Right. DC, yeah, exactly. AC goes positive half the time and negative half the time, and it goes back and forth like that. Rectifiers take that signal and turn it into something that's only positive. Just save a little bit of room here. So after the rectifier, there's another type of device, which is called a filter. And the filter makes the signal a little bit smoother. So it's still not perfect, but you get a signal that ends up looking kind of like that. Okay? So it's getting closer to that flat DC line that we're looking for, but it's not quite there yet. And then the last step is one more device called a regulator. And the regulator takes that final step from that wavy line to the nice flat DC line that we're looking for. Okay? So again, the purpose of a power supply is to go from a high voltage AC signal to a low voltage DC signal, and it does that gradually with these steps. It goes from the high voltage AC to low voltage AC. The rectifier then gives us a signal that's only positive but has these big humps in it. Then we use a filter to smooth out some of those humps, and finally a regulator gives us that final smoothing to get to the nice flat line. Okay? So tonight we're going to talk about a couple of different types of rectifiers and their advantages and disadvantages. Next time we'll talk a little bit more about filtering, and we'll talk about some regulators. Okay? So we'll discuss a little bit of filtering tonight also. So that's the general block diagram for every power supply that's out there. So any questions about that? Okay, cool. So then, let's talk about the three different types of rectifiers. Okay. So the first type of rectifier is the simplest kind that there is. Basically, you have a transformer here, and then you've just got a single diode, and then you've got this resistor over here, which is called the load resistor. Now this is a stand-in. This represents the thing that you're trying to power. So if you were charging a battery, this would represent the battery that's being charged up. If you were powering a computer, this would represent the computer. Basically, a lot of different things behave kind of like resistors. So we just use a resistor as sort of a stand-in or a dummy that represents the real thing. So in the real world, you would have the actual device that you're powering. In our case, for the simplicity of a diagram, we're just drawing a resistor. And in your lab, you're just going to be drawing the resistor, or you're going to be using a resistor in your circuit. Okay. So this is the simplest type of power supply that is available, or I'm sorry, the simplest type of rectifier. This is called a half-wave rectifier. So what happens is that basically you've got an AC signal. So the AC signal has a positive voltage here half the time and a negative voltage here half the time. So to understand what's happening in the circuit, we have to look at both cases. The case where we have a positive voltage here and the case where we have a negative voltage here. So we'll look at them one at a time. We'll start by looking at the case where we have a positive voltage here and see what's happening with our resistance. So when we have a positive voltage here, that means that we've got a positive and a negative voltage across the diode like that. So is that diode forward biased or reverse biased?
Forward.
Forward, perfect. So does that mean current flows?
Yes.
Yes, exactly. So the current is going to flow through there, it's going to flow through the resistor, and end up back at the transformer. So if we had an input voltage that looked like this, then our output voltage would go up when our input voltage was positive. Now let's say that we had 10 volts on our input here, 10 volts there. This voltage is going to go, and the current is going to flow through one diode. So how much voltage is it going to lose across that diode?
0.7.
0.7 volts, perfect. So how much is going to be left across the resistor?
9.3.
9.3, exactly. So our output voltage would look something like this. It goes up, it doesn't go quite as high as the input. There's that 0.7 volt difference there. Okay? Now let's look at the other case where we have a negative voltage up here and a positive voltage down there. Now we've got a negative voltage on that side of the diode and a positive voltage on that side. So is the diode forward biased or reverse biased?
Reverse.
Reversed. So is current going to flow?
Nope.
No, exactly. So there's no current flowing across the resistor. How much voltage do we have across the resistor when there's no current?
0.
0, exactly. So in this case, we're going to have 0 volts across our resistor. And then eventually the voltage is going to flip back around, and we're going to have positive voltage like that again, and then the output is going to be 0 again, and so on. Okay? So hopefully now it's becoming a little bit clear why they call this a half-wave rectifier, because we get the positive half of the input wave, and then we just get rid of the other half. So we're only capturing half of our input signal. That's why they call it a half-wave rectifier. Yeah? Not quite. And let me talk about why that is.
Still EC.
Right. So let's talk about the filtering for just a minute. So oftentimes, as a filter, people will use a capacitor and put that in parallel with the resistor, okay, with the load. And what the capacitor does is that it gets charged up when the voltage goes positive. So it gets charged up, and then when the voltage goes negative, the capacitor discharges, but it discharges slowly, okay? So it goes down something like that. And then the next time the positive wave comes, it gets charged up again, and then it goes down slowly. And then it gets charged up and down slowly like that, okay? So this is how we end up with that filtered wave that I was talking about before, okay? So it's not perfectly flat. We need the regulator to make it perfectly flat, but it doesn't go down to 0 anymore, okay? So this is the filtered output. And there's a term for the amount of change from the top to the bottom. So the amount that this signal wiggles around, that's called the ripple. Okay? So do you think it's good to have a lot of ripple or a small amount of ripple?
Small.
Small amount, exactly. Because remember, we're trying to get to that perfectly flat line, and a perfectly flat line has no ripple. So the less ripple we have, the closer we are to our end goal. Okay? So we're looking for a small amount of ripple. All right, so that's pretty much what's happening with the half-wave rectifier. Any questions about that? Okay, so then the next circuit that we're going to look at, again, starts with the transformer. This type of transformer is special. It's got an extra wire right in the middle. This is called a center tap transformer. Okay, and this type of rectifier has 2 diodes. And then the load is over here.
Oh, okay.
And this is called a full wave rectifier. So again, we're going to look at the two cases of the voltage, one where we have a positive voltage at the top, and then one where we have a negative voltage at the top. So we can start with the positive voltage up there. Now, we got a positive there and a negative, positive and negative. Like that. So the electricity comes to this first diode. Is the diode forward biased or reverse biased?
Forward.
Forward, exactly. So the electricity flows through here. Now it gets here, it's going to come and try and go through this next diode down here. Is this one forward biased or reverse biased?
Reverse.
Reversed. So the electricity can't go down through that one. Instead, it all has to go this way through the load resistor. And then it comes back around and it ends up back over here. So it's flowing down this way through the load. So if we look at our input wave again, let's say we had 10 volts at the input again. Now in this case, we've got a single diode drop again, but we're using this center tap transformer. So the center tap transformer takes the whole 10 volts and it divides it in half. So you get 5 volts up there and 5 volts down there. So now we've only got 5 volts to work with and we lose 0.7 volts there. So how much voltage do we have across our load?
4.3.
4.3. Exactly. So that means that our input wave, or our output, goes something like that. So it goes positive, but it's less than half of our input. Okay? And now we can look at the case where the voltage is reversed. We got a negative voltage up there and a positive down there. So in this case, the electricity starts out here and it tries to go through this diode. Is this one forward biased or reverse biased?
Now it's forward.
Now this one is forward, exactly. So the electricity flows through there. It comes up here, it gets to this point. It tries to go left through this diode, but this one is reverse biased now. So it can't go that way. So it all has to go down through the load again. And then back up and around to the center. Okay? So again, we have pretty much the same situation. We're starting with 5 volts, we lose 1 diode worth, so we're left with 4.3 volts on our load again. So now we get an output that looks like that. So this is a good thing in one way, because now we're capturing both the high positive part of our input and the negative part of our input. So in that sense, it's good, but at the same time, the output voltage is much lower than it was before, because we're only starting with half of the input voltage. Okay? When we put a filtering capacitor in parallel with our resistor there, we end up with a filtered signal that looks something like this. So
less ripple.
yeah, there is less ripple, exactly, because these peaks are closer together, and so the capacitor has less time to discharge. Another way to say that is that the output frequency is doubled, right? So it's a higher frequency, so the capacitor has less time to discharge. So less ripple, so that's a good thing also. Okay? Questions about the full wave rectifier? Okay, and then the last type of rectifier we're going to look at is called the full wave bridge rectifier. So again, it starts with the transformer. This one has 4 diodes. Okay. And then the load resistor is over here. Like that.
So no center tap.
No center tap, that's right. No center tap on this one. So
Now we get
yeah, so again, we'll start with the positive voltage and the negative voltage there. So diodes are biased like that. Electricity starts here. The right diode is forward biased, the left one is reversed. So all the electricity goes to the right, goes through there. Now, again, this bottom diode is reverse biased, so the electricity can't go that way. It all has to go through the load. Comes up there. Electricity always goes towards the lower voltage, so it's going to go down this way, and then it's going to end up back at the other side of the transformer. So if we're looking at our input, our output, so we're starting with 10 volts again. We start with 10 volts, and this goes through one diode there and a second diode there. So it loses 2 diode drops, or 2 times 0.7 comes out to be what? 1.4. So we start with 10, we subtract 1.4, we're left with 8.6 volts. So we have 8.6 volts across the load. So our output should look something like that. In the opposite case, where we have a negative voltage up there and a positive voltage down there, the electricity starts here. The right diode is forward biased here, so the electricity goes to the right. This one is reverse biased, so all the electricity goes through the load. Yeah, exactly. And then it comes up and around here, and it ends up going down. Oh, I'm sorry. It goes up this way and back to the opposite side of the transformer. Okay, so again, we're starting with 10 volts. We're losing 2 diode drops, so we end up with 8.6 volts on the output. So the output looks something like that. So we're capturing both the positive and the negative half of our input signals, and the output is just a little bit lower than the input. Okay, about 2 diode drops lower. This is the Okay. So,
I have
yeah.
a question. So at the junction, when it's jumped over, it's gone through the load on the positive side, it jumps over, it comes back into the bridge,
Yeah.
comes back in right there. Why does it go on the positive side down to that diode and not through the other one? Because they're both positively biased at that point.
We're talking about the green line here.
Yes, yeah, just the green line.
Right. So it's already lost some voltage, and it always goes towards lower voltage.
Okay, goes towards lower voltage.
Yeah.
Okay, got it. I see. Okay, that makes
And then,
sense.
again, when you're filtering this one, the capacitor gets charged up and then discharges. And so you have the higher frequency like we did on the full wave rectifier. So again, you end up with less voltage than the half wave rectifier, less ripple voltage. So questions about that? Okay, then I'll just remind you that we have a little bit of homework to do. We have the, I believe that there's a power supply quiz. You can get started on that, and you can work on it a little bit more after next lecture as well. In terms of the lab tonight, you guys are going to get to build a half wave rectifier, a full wave, and a full wave bridge. So yeah, so that's quite a lot of circuit building. So unless there's any questions, I will let you get started. All right. Thank you very much. Yeah.
They need transformers, right?
Yes. Yeah. Okay. Yeah, that's right. There's a couple of notes about the transformers. The transformers actually have circuit breakers on the backs of them. So you want to make sure that those circuit breakers are pressed in. That way the electricity will be flowing. If you hear it click, that means one of them blew. That means something's wrong with your circuit. Okay, so turn everything off, check your circuit, figure out what's going on, and then wait for about a minute. You'll hear another quieter click, and then you can push the transformer or the circuit breaker back in and turn the transformer back on.
Okay, sorry.
And then the only time you have to measure the transformer's output voltage, or VS, is in the very first circuit. So you can take that one measurement and then copy that over for all the other circuits in the lab. And then finally, a couple of times in the lab, it asks you to calculate the expected DC voltage that's coming out. There are formulas at the beginning of the lab that you can use to figure out what that expected voltage is. So if it's asking you about expected VDC, use those formulas from the beginning of the lab. Okay? Any questions about that? All right, then you can take a break if you want, or you can just get started on the lab. It's up to you.